Good afternoon. Welcome to the class of optical communication, and today we will discuss the topic absorption and the scattering loss in a optical fiber cable. Now, I am Mr. Himanshu Nagpal, Assistant Professor in EC Department of AKGEC Ghaziabad. So, to start with the before we start with the absorption and the scattering losses, we must know the term that is a attenuation, and this attenuation of optical fiber is the loss of the signal in the optical fiber cable, and there are number of factors which causes the attenuation in the optical fiber cable, and one of the factor or one of the two factors which are responsible for the attenuation, that is the absorption and the scattering loss, which we will discuss today. So, signal attenuation within an optical fiber cable can be due to the metallic conductors, and it can be expressed as a logarithmic unit of the decibel, and this attenuation can be expressed in terms of decibel. So, and this attenuation is equal to the, can be written as 10 log of P input divided by P output, and this is expressed in terms of dB. Clear? So, this decibel is generally used for comparing the two power levels, which may be defined as a particular optical wavelength as a ratio of the input power, that is Pi, into the optical fiber to the output power, that is P out. Let us say, if I say this is an optical fiber cable, and the input which is I am providing, that is Pi, and the output which is I am getting, that is Po. So, attenuation in this optical fiber will be equal to 10 log of P out divided by Pi, and this can be expressed in terms of decibel. So, there are number of mechanisms which are responsible for the signal attenuation within optical fiber cable, and these mechanisms are generally influenced by the material composition, preparation and the purification technique, and the waveguide structures. And there are number of further factors. These factors, there are number of further factors which can be categorized into different major areas which causes the attenuation. Like, the area is material absorption, material scattering, and this scattering is further classified into two types, that is linear and the non-linear, and the another factor, that is a curve and micro bending losses, which also causes the attenuation, mode coupling, radiation loss, and loss due to the leaky modes. These are all factors or areas which mainly contribute to the attenuation of the signal, and there are number of other factors which are also added to the attenuation or loss in the optical fiber cable, that is loss due to the connector and loss at the splicing, and this splicing is the process of joining the two optical fiber cable. When I want to join the two optical fiber cable, we use the process or technique, that is a splicing, and during the fusion of two optical fibers, the technique which is, or the process which is known as, that is splicing, and this splicing also causes the signal loss in the optical fiber cable. So, attenuation can be expressed, which I have already told you, this attenuation can be expressed in terms of decibel per unit length, that is dB per kilometer, and this one is equal to alpha dB multiplied by length of optical fiber cable is equal to 10 log of P input divided by P out, and this alpha is the attenuation of optical fiber cable per unit length, and this length can be expressed in terms of kilometer. Clear? So if I want to calculate the overall attenuation, then this one is the overall attenuation 10 log of Pi by P out. Now the one of the factor which is responsible for causing the attenuation, that is the absorption, and this today we will discuss the topic, that is the material absorption in silica glass fiber, and this is the factor which contributes in the signal loss. So material absorption is a loss mechanism related to the material composition, the fabrication process for the fiber, which results in the dissipation of the sum of the input optical power as a heat in the waveguide. And so as it is, I told you that this is a material absorption losses. So this material absorption related to the material composition and the process for the fabrication process for the during the manufacturing of the fiber, and this results in the dissipation of the sum of the input power as heat in the waveguide. Now if I say this absorption is due to the material composition, so material composition can be of two types, means due to the extrinsic material or impurity present in the silica fiber, and some absorption due to the molecules present in the silica glass fiber. So this is also known as the intrinsic absorption. So this absorption can be classified into two types, intrinsic and the extrinsic. This intrinsic absorption caused by the interaction with one or more major components of the glass only, means fiber which is made up of the silica glass, and the interaction between the one or more of the major components of the glass only, and this extrinsic absorption caused by the impurities present within a glass. Clear? The first one is the intrinsic absorption. So this intrinsic absorption is generally a pure silicate glass has little intrinsic absorption due to its basic material structure in the near infrared region. So you will see here that two major intrinsic absorption mechanism have two windows, that is low intrinsic absorption observed at 0.8 to 1.7 micrometer wavelength. The effect of these process can be minimized by the suitable choice of both core and cladding composition. So as intrinsic absorption is mainly due to the component present within a glass fiber, and there is not an impurity, only the component which is present inside the in the silica glass fiber. Clear? So this type of material absorption can only be minimized by the suitable choice of core and cladding composition. For instance, in some non-oxide glasses such as fluorides and chlorides, the infrared absorption peaks occurs at the longer wavelength as compared to the other oxide glasses. Clear? So non-oxide glasses such as fluoride and chlorides, the infrared absorption peak occur at much longer wavelength, which are well into the infrared, far infrared to the 50 micrometer, giving a less attenuation to the longer wavelength. Clear? As compared to the oxide glasses. So this one is the graph which I have taken from the John M. Senior book. This graph represents the total attenuation with respect to the photon energy and also with respect to the wavelength. And you will see that here that this loss, as the wavelength increases, this loss, overall loss is decreases, and after the wavelength of 1.7 micrometer, this loss is also increasing. Now with the range of if I talk about the absorption losses, there are two types of absorption loss, two windows of absorption. It is the ultraviolet absorption and the infrared absorption. You will see here that as the wavelength increases, ultraviolet region, the absorption at the ultraviolet region also decreases, but after the wavelength of 1.5 micrometer, the infrared absorption increases. So this one is the window, this one is the area where the overall absorption is less as compared to the other region, clear? And this area generally represents the wavelength of two windows, that is 1350 nanometer window and 1550 nanometer window, over which the overall absorption is less as compared to the window at the 800 nanometer. Now next one is the extrinsic absorption. As we know that the optical fibers are prepared by the some conventional melting techniques, and during the manufacturing of the fiber, some of the impurities can be present during the, can be incorporated into the optical fiber, not intentionally, but it can be by accidentally, it can be incorporated during the manufacturing process. So a major source of signal attenuation is extrinsic absorption from the transition metal element impurities. Some of the transition metal element impurities are chromium, copper, iron, nickel, manganese. These are the transition metallic ions which causes the absorption at a peak wavelength of 625 micrometer, and this copper provides a attenuation maximum at the 850 micrometer, iron provides a maximum attenuation at the 1100 nanometer, clear? So these transition elements combination may be related to the acceptable levels by, and this acceptable level generally represent in terms of ppm, parts per million. So these impurities generally expressed in the pure material expressed in terms of the parts per million, and these impurities can be minimized in the optical fiber cable by using a improved glass refining techniques such as vapor phase oxidation, which largely eliminates the effect of these metallic impurities. So by improving the fabrication techniques, we can reduce the extrinsic absorption by removing the impurities which generally occurs. This another major extrinsic absorption mechanism is caused by the absorption due to the water, means that is a hydroxyl ion which are dissolved in the glass. So another portion, another impurity, or you can say another composition which contributes to the absorption, that is the hydroxyl ion, which generally can be included into the optical fiber cable manufacturing, during the manufacturing of the optical fiber cable. So you will see here that the absorption spectrum for the hydroxyl ion, you will see here this is the first over third overturn, this one is the second, and this one is the first. Means you will see here that the due to the hydroxyl ion, this wavelength there will be a higher attenuation, and at this wavelength due to the hydroxyl ion attenuation is less as compared to the higher wavelength. So if we want to use the optical fiber cable at the higher side, at the higher wavelength, so we have to reduce the or minimize the hydroxyl ion. We have to minimize the hydroxyl ion in the manufacturing of the or during the manufacturing of the manufacturing of optical fiber cable. So these hydroxyl ion must be removed during the manufacturing of the optical fiber cable. So this one is the overall measured attenuation spectrum for an ultra loss single mode fiber with the calculated attenuation spectrum for the sum of the loss mechanism contributing to the overall attenuation. So you will see here that this one is the experimental, this dark line is the experimental attenuation, clear. So you will see here that overall during the experiment, overall maximum attenuation is generally observed at what? At this wavelength, at around 1.415 something, clear. So at the minimum around 1550 nanometer, the attenuation is minimum, and around 1350 nanometer attenuation is less, and around 800 nanometer attenuation is this one. So you will see here generally we always prefer to have a optical fiber cable which is operating at a higher wavelength to get the minimum attenuation or minimum loss. So minimum loss due to or absorption loss, clear. So next factor which is responsible for the attenuation in the optical fiber cable, that is the scattering loss, and this scattering loss is generally arise due to the impurities present or due to the small particle present inside the optical fiber cable, or you can say small inhomogeneity, small scale or large scale inhomogeneity present in the silica glass optical fiber cable. Clear? So this scattering loss arises from the microscopic variation in the material density, from compositional fluctuation, and from structural inhomogeneities or defects present occurring during the fiber manufacturing. So generally this scattering losses occurs due to the inhomogeneity, structural inhomogeneity present or defect present in the during the optical fiber cable, manufacturing of the optical fiber cable, also due to the compositional fluctuation or microscopic variation in the material density. There may be a fluctuation in the material density that also causes the scattering losses, and if I say compositional fluctuations also contributes the scattering losses. So this scattering loss is further divided into two types, that is a linear and the non-linear. Linear and non-linear. So this linear is further divided into two types, Rayleigh scattering and the Mie scattering, and this non-linear is further divided into two types, that is stimulated Brillouin scattering and the Raman scattering. So first of all we will talk about the linear scattering loss, and in this linear scattering loss we will further study about the Rayleigh and the Mie scattering. So this linear scattering mechanism cause the transfer of some or all of the optical power contained within one propagating mode to be transferred linearly into a different mode. Let us say if I say there are two modes which is present inside the three modes which is present inside the traveling inside the optical fiber cable. So due to the linear scattering loss, this mode can transmit its energy to the other mode, means this mode can transfer its energy to the another mode. Clear? So transfer of sum of all of the optical power contained within one propagating mode to be transferred linearly into a different mode. Clear? Linearly means if I say input power is less, linearly graph means this one is the input power and this one is the output power. Input power less, so less energy will be transmitted into the optical fiber cable. As the input power increases, the more of the energy will be transferred to the optical, next more energy will be transferred to the another mode. Clear? So this process tends to result in a attenuation of the transmitted signal, as a transfer energy or transferred mode may be leaky, maybe to a leaky or radiation mode, which does not continue to propagate within a fiber core but is radiated from the fiber. Okay, so it may happen that one mode which is propagating inside the optical fiber cable transfer its energy to the other mode, to the another mode, and this another mode may be a leaky or radiation which will not propagate, does not continue to propagate inside the optical fiber cable, and but is radiated outside, it's radiated out of the optical fiber cable. So scattering is what? If I say this is the optical fiber cable and one of the material which is present inside the optical fiber cable is particle which is present, so when the light is incident on this optical fiber cable, this light becomes scattered. Clear? So after scattering, if I say this is a frequency f1, so after scattering the frequency will not be changed. So in linear process there is no change of frequency on scattering. So this linear loss can be categorized into two types, Rayleigh scattering and the Mie scattering, and both results from the non-ideal physical properties of the manufactured fiber which are difficult to eradicate or which are difficult to minimize. Clear? So this linear scattering is generally due to the non-ideal physical properties of the manufactured fiber. If I say this is a ideal characteristics, optical fiber is means there is no loss, that is P in, output will also P in, that is a ideal case. But we always know that the no such ideal material is present in the optical fiber cable. So some of the non-ideal property which is of the optical fiber cable causes the scattering, and this scattering is the linear scattering. Due to the non-ideal properties, it is difficult to or impossible to eradicate at the present. Clear? So Rayleigh scattering is a dominant intrinsic loss mechanism in the low absorption window between the ultraviolet and the infrared region. It results from the inhomogeneities of the random nature occurring on a small scale compared to the wavelength of the light. Means it generally occur due to the what? Let's say if I say this is a optical fiber cable and this one is the inhomogeneity present inside the optical fiber cable. This is a inhomogeneity, or you can say particle. Clear? So when the size of this particle is very less than the wavelength of the light, So this type of then there will be scattering, and this type of scattering is comes under the Rayleigh scattering, when the inhomogeneity occurred on a small scale as compared with the wavelength of the light. This inhomogeneity present inside the optical fiber cable contributes to the refractive index fluctuation, and also arise from the this homogeneity can be categorized, can be contributed into the refractive index fluctuation, and this also arise from the density and the compositional variation which are frozen into the glass lattice on cooling. Means this inhomogeneity contributes to the refractive index fluctuation, and this homogeneity can also be arise due to the density and the compositional variation which are frozen into the glass lattice on cooling. Means this is one of the technique during the manufacturing of the fiber. So during the manufacturing of the fiber, this process we have to follow, and do the process which I am following, that causes the compositional variation, and this compositional variation causes the Rayleigh scattering. So this compositional variation may be reduced by the improved fabrication technique, clear, but index fluctuation caused by the freezing in of the density inhomogeneity cannot be avoided, as this is a process which we have to follow, and this due to the process this process which I have to follow for the manufacture of the fiber cable, and this process can also cause the inhomogeneity, clear. So this you will see here, this is a small particle, and this small particle, when light enters into the strike onto this molecules or small particles, the light wave get scattered in almost all the direction, clear. So this scattering due to the density fluctuation which is in almost all the direction produces an attenuation inversely proportional to the 1 by lambda ki power 4, and this Rayleigh scattering can be Rayleigh scattering can be measured by its coefficient, that is gamma r, and this gamma r is the Rayleigh scattering coefficient, and this Rayleigh scattering coefficient is inversely proportional to the lambda ki power में 4. If I increases the lambda, the Rayleigh scattering coefficient, the magnitude of Rayleigh scattering coefficient get decreases. So Rayleigh scattering coefficient is also related to the transmission loss factor of the fiber, and this is represented by is equal to e की power में minus gamma r multiply में L, and this L is the length of the optical fiber cable, and this gamma r is the Rayleigh scattering coefficient, and here N is the refractive index of core, P is the photoelasticity, beta is the isothermal compressibility, K is the Boltzmann constant, Tf is the effective temperature. Next one is the Mie scattering. This Mie scattering is caused due to the inhomogeneity which are comparable in size to the size of the is comparable to the wavelength of light. This can be these result from the non-perfect cylindrical structure of the fiber. This may be caused by the particle size is large as compared to the wavelength, and this can be caused by the fiber imperfection such as irregularity in the core cladding interface, refractive index differences along the length of the fiber, diameter fluctuation, strain and bubbles. These all can cause the rise of the inhomogeneity present inside the optical fiber, which are of length as compared to the wavelength of the optical fiber cable. So when the scattering homogeneity size is greater than the lambda by 10, this scatter intensity has an angular dependence which is of very important value, and this homogeneity can be removed by can be removed or minimized by removing the imperfection during the glass manufacturing process, carefully control extrusion and the coating of the fiber cable. This will reduce the strain and the diameter fluctuation, increasing the fiber guidance by increasing the relative refractive index. These are the methods by which we can remove or minimize the inhomogeneity inside the optical fiber cable. So in the next lecture we will discuss about the nonlinear scattering. Today we have discussed the absorption losses and the linear scattering losses, and the book which I have referred for preparing these slides and for showing the graphs from the John M. Senior, and the book title name is the Optical Fiber Communication Principle and Practice by the author is John M. Senior. Thank you.